Okay, pues welcome to the second talk of the Apply Analysis and Probability session. This is session number 3. And the speaker is Jorge Alfredo Esquivel Avila of the UAM Azcapotzalco. And Jorge, the screen is yours, and the audience too. So go ahead.
Okay, thank you very much, Jorge, for the invitation, for the opportunity to talk this time. The subject of this talk is, the title is a differential inequality and the law of its solution. Okay, this is the context of the talk. I will talk, first. I will say something about the problem, and I will do some related applications. Next, I will talk about the main result and some remarks and reference. Okay, so this is the problem. The problem consists to find how any solution of this differential inequality can blow up in a finite time. So there exists when the problem consists to find sufficient conditions in order to find some finite time t star such that the solution of any solution of this differential inequality goes to infinity as t times 2t star. This coefficient of in the differential inequality, alpha, beta, gamma, and delta are constants. And how this inequality comes, where it comes from? Well, some application is this abstract formulation of a type, a wave type equation. So when we study an evolution equation like this, for example, this an abstract evolution equation, second order in time, we have several questions. This is an abstract formulation. We have to give a functional framework in order to study this problem. So here P, A, B are operators. Some of them differential operators. F is a nonlinear term. They are defined in this phase space. The problem is defined in this phase space. The problem consists to find a solution U, which depends on these initial conditions U0 and U1, and we have this impedance. So when we study an evolution equation like this, we have natural questions like this. First of all, is to find the answer the uniqueness and existence a uniqueness of local solutions given a pair of initial conditions. So the first problem is to find exactly in what sense we are going to understand the solution. So is to find what space is this one. So when we have that solved, then the next question is if we can extend the maximal time of existence up to infinite or not. When the maximal time of existence is infinite, we say that the solution is global. And another question is to find what happens with the solution goes to infinity. So that means to find out the asymptotic behavior for large times. If the maximal time of existence is finite, then sometimes in this kind of equations, in infinite dimensional spaces, sometimes this is due to the blob of the solution with the time it tends to the maximal time of existence, and the blob is in the norm of the phase space. One method to study the blob is through the differential inequality like this. Like this is one of the several methods. In applications, this function psi of here in the differential equation, in the applications for this abstract wave equation, is this function is a function of the norm in some space S of the solution. Okay, so that's where the inequality comes from. I will talk briefly about the formulation of this example, this abstract example. So when we have the operators A, B, and P, we define bilinear forms, and through these bilinear forms, we define naturally norms. And if we assume these conditions, the norm in the space HA is stronger than the norm in the space HP. And the nonlinearity satisfies this inequality, where this R is a measure of the nonlinearity of the function f. And also we are going to we assume that this function is potential. So the potential is f, capital F. But we have that assumptions and that abstract framework, we can define a solution. We can define which is called a weak solution. In terms of the bilinear forms, the solution of this equation is understood in this sense. So satisfied in this weak sense almost everywhere for every time and for every W in HA. So given the initial conditions, the problem is to find the solution in this sense. So also we are going to require that the solution is satisfied as an energy equation. This is the energy in some T naught fixed time T naught is equal to the energy in any time plus this dissipative term. And this is a damping term. This is the dissipation. And the energy is defined by this formula. When we have present here the nonlinearity F, which is the cause of the blow-up, the blow phenomena. So if the maximal time of system is finite, we are going to consider that this is due to the blow-up in the phase norm, in the phase in the norm of the phase space. So in order to apply the differential inequality of this talk to this example, we require that this operator B, which is here, this operator B, has this form: is delta, constant delta, positive constant delta, times the operator P. And the function psi is exactly the square norm of the solution in the space HP. And the blow-up time obtained, the blow-up time obtained by this inequality is always an upper bound of the maximal time of existence of the abstract equation. A couple of examples of the abstract example are these. I will just say some few words about that. This is the generalized Boussinesq equation in the whole space Rn. This is the Cauchy problem. And if we apply the inverse operator of the Laplacian we find exactly what we want to have. I mean, we have exactly the form of the abstract formulation. So we can define the operator P, the operator A, and the spaces associated to those operators, and the corresponding norms. So in that sense, we can apply our results to study, for instance, this problem. Another example, very frequently studied in the literature is the Kirchhoff equation. When we have two nonlinearities, besides the nonlinearity in the right hand side of the equation, G, we have another nonlinearity phi here. So this is a boundary, initial boundary problem. We define a phase space. We assume some condition of the nonlinearity of the right hand side of the equation, and this is the nonlinearity of the term here. This is a typical nonlinearity in this Kirchhoff equation. So when we put in the abstract form, the abstract framework of problem, the operator P is the identity, the operator A is the Laplacian, and the nonlinear term is a sum. It's a sum of two nonlinearities where there is a competition of these two linearities. And this inequality gives us the opportunity to get exactly the blow-up property of the Kirchhoff equation. If we reverse this inequality, it can be proved that there is no blow-up of this phenomenon. There is no blow-up phenomenon in this equation, and precisely exists a global attractor of the solutions of this equation. But I am not going to talk about this problem of attractors. I will talk just about the blow-up property. So here we have some references about this blow-up property. Here there is a recent book by Korpusov where there is a review of in that book there is a review of the several methods to study the blow-up phenomena. One of them is which is based in differential equations, but differential inequalities. And there are more methods. And in this book also there are several applications to the equations in the mathematical physics. So one method, the origin of this methodology of differential inequalities goes to the works of Professor Howard Levine. This is the well-known concavity method. These are two classical references of Professor Levine, where this concavity appears for the first time. After this concavity method, there appear in the literature several generalizations of this methodology, and one famous is this paper. One famous contribution is this paper by Kalantarov and Ladishonskaya, where they study quasi-linear equations of parabolic and hyperbolic type, and they constructed differential inequality to study exactly the collapse. Here the name is collapse, the blob of the solutions of a class of these equations, and they study this phenomena. Then there are many references about this property, but I am just write here just the main what I consider the main references, the main contributions in this subject. There is another important contributions by Korkusov around the study of Kirchhoff and wave equations. And more recently, there is another nice contributions by Dimova, Kolkovska, and Kutev. These two, the references 5 and 6 are in the were studied, they study the blow property with the emphasis in the what happened with the initial energy is positive. That's a current subject in this matter. So I will define these functions. I will talk later about this. I will require these functions to find the result. And this is the main theorem. The main theorem says that if we have this inequality, the first inequality, and the second is that means that if delta is positive, if delta is strictly positive, that we require also that the initial this subindex not means that the function valued in time t equals 0. So that means that in time t equals 0, we require this inequality. This is the only condition that we require in order to get the blow-up. If this condition holds, then we show the existence of a non-empty interval. This non-empty interval is contained in this here. And here we have function phi, which is defined here. And phi naught is the value at t equals 0. With the following consequence: the existence, when we prove the existence of this non-empty interval, and when this gamma is one of the coefficients in the inequality. When that coefficient belongs to this interval, then we prove that the solution blows up in finite time. That's the theorem, and this theorem is a generalization of the theorems given in these references in several senses. We can besides the existence of this the interval, blow interval, I call blow interval. I can give I can calculate the values of the numbers a and b in terms of the functions that I introduced here. I can calculate it here in terms of this mu star and lambda star, which are not exactly known, but are in between these two values. We can have also some properties. The blow-up time is strictly increasing with respect to the damping term. The size of the blow-up interval is strictly decreasing with respect to the damping term, which is naturally expected. Also, what we have here is that the main point, I mean the main ingredient that produce the blow-up is this value, the derivative of the function psi at t equals 0. This function is still the blow-up time is strictly decreasing as this with respect to this number, and the blow-up interval is strictly increasing with respect to this number. We have some bounds. We have a lower bound of the blow-up time in terms of this difference, which is positive because this It's positive because of the condition A. And we have these limit values. For instance, this is very it's important to notice that when this number is very large, we have almost an instantaneous blow-up time. Almost at time t equals 0, the solution goes to infinity. So, and that because of this property with respect to this derivative, because of this, we can have this interesting corollary. Given any number gamma, which is one of the coefficients of the inequality, we can find this number large enough in order that this number gamma always is contained in the blow-up time, and consequently we have the blow-up of the solution. So this corollary is give us the essential ingredient, which is this number to get blow-up. And well, I will skip the proof because I think I don't have a lot of time more. So I will just mention some remarks. Why I say that this is an extension of the results in the literature? Because well, one important ingredient is this delta. No, is this sorry, is this gamma? Is this gamma? Gamma was considered 0 in the first reference by Ladyshenskaya and Kalantarov. But this in applications of hyperbolic equations, this gamma is proportional to the size of the initial energy. So since this current problem in this in hyperbolic equation is to find the blow-up conditions for any value of the initial energy, for that reason, it's important to consider that this gamma be positive. And this is the and the corollary gives us exactly a nice result about that. Another important extension with respect to the results already published is that we consider this delta strictly positive, because in this sense we are we can handle problems with this with dissipation, which are not in many papers are not considered. So many papers the blow is only studied for conservative problems. And another point is that this another coefficient of the inequality gives us an estimation of the blow interval. So that the reason this beta must be positive, because in that sense we generalize the results already in the literature. So I have this some references here where the talk was based. Recent reference where we study the differential inequality and give some applications in abstract wave equations. And I think that my time is over. Thank you very much.
Thank you, Jorge. If there are questions, please let me know. Write in the chat or opening your microphones if they are not open. Any questions? Anybody has questions? Your microphones are open now. You can ask your questions directly. No questions? Okay. Well, Jorge, thank you very much for your talk. We have a few minutes before the next one. Thank you. The next one